In this video, I'm going to talk about a standardized effect size, which is Cohen's d, and I presented it in the textbook relevant to one sample t-test because it's so important to interpret statistical results in the context of effect size. You might recall the reasons we do statistics that I described way early in the textbook. One of them is to estimate the magnitude of an effect, and this Cohen's d is part of that job, estimating how big of a difference there is. So we know there is a difference with a very high level of probability, and now we want to know, is the difference a big one? Cohen's d can help us get some context with respect to the magnitude of effect. And Cohen's d equals the sample mean, which is x bar here, minus the non-sample mean, or some people pronounce this mu, or sometimes it's a population mean. But in this study where I looked at the difference between my long-held impression of 8 hours of sleep per night on average versus the sample mean, this is just simply a non-sample mean. It's not really a population mean, the 8.0, but it could have been. So then we have divide by standard deviation, and dividing the difference by the standard deviation makes it a standardized effect size. So let's look at the actual example. We have the sample mean of 7.31, which was estimated by Kripke et al., and we have here the non-sample mean, which is my long-held impression of 8 hours. And that difference is divided by the sample standard deviation, which was 1.06. So then we end up with a negative value here because my long-held impression is larger than what the sample mean was, and divided by 1.06, and that gives negative 0.65. So is that big? Well, it's 65% of a standard deviation. And a difference between two means, or a mean and a non-sample mean, that would equal a full standard deviation, I would say is very large, because it's not observed very often. And think of the standard normal distribution. One standard deviation is really quite a large percentage of the distribution. So it doesn't happen very often. And Cohen has actually provided guidelines to interpret Cohen's d. And right here I've got 0.20 between straight lines. These straight lines mean an absolute value, so whether it's negative or positive, it doesn't matter. It's an absolute value. 0.20 is small, 0.50 is medium, and 0.80 is large. And because I found a difference of negative 0.65 between the sample mean and my long-held impression, it would be considered somewhere between medium and large. So I was off the mark with my long-held impression in terms of the difference between the sample mean and the non-sample mean expressed in standard deviations. So it's 65% of a standard deviation. And again, I mentioned in the textbook, whether it's negative or positive is arbitrary. Technically, I could have written 8.00 minus 7.31, and I would have got a positive 0.69. You just have to keep in mind what your hypothesis is and how you want to express the difference between the two. And in this case here, I've said that my estimate is an overestimate of the sample mean. So that's Cohen's d. It's going to come up several times in this textbook, especially in the test of the difference between two means and other chapters relevant to the difference between means. In this case here, it's expressed in the context of a difference between the sample mean and the population mean.